Okay, today we're going to have a look at common curves in 3 dimensions. So we should be able to recognize from our work with further functions in Extension 1 Year 11, we might be able to recognize some common curves. So it's important that we learn how to recognize and sketch these curves in their parametric equations without needing to convert them to Cartesian form, plus be able to convert each of these into Cartesian form if needed. Once you're familiar with them, you'll be able to use the basis of you'll be able to use these for the basis of harder curves. Now, of course, if you're stuck, just convert it to Cartesian form. It's just going to take you longer, and it means it's going to take you longer to complete the exam. But it's important that we recognize these. So if I've got y as cos t and sine t, that's a circle, center of the origin, radius 1. You don't necessarily have to know this one, but this is the equation of an ellipse. If you've got an A and a B there, it's kind of like a squashed circle. X is t, you need to know this one. If x is t and y is t squared, this is the equation of a parabola. A rectangular hyperbola is a normal hyperbola. You've got x is t and y is 1 on t, nice and easy. Don't have to know this one, but a hyperbola, some people I think call it a non-rectangular hyperbola, but it's just a hyperbola. And this is what hyperbolas normally look like. This is the special case of a hyperbola. It's a nice and easy hyperbola in which the two asymptotes are the x and y axis, or they're perpendicular to each other, and that they're parallel to the x and parallel to the y. But most hyperbolas look like this, and in the old Extension 2 syllabus in a topic called conics, you learn all about these, but sadly they got rid of those because, I'm pretty sure because they're getting rid of applications of graphing because of computers, and you can just graph them on a computer. Anyway, let's have a go at just some easy transformations. So let's consider the parabola y as 2x squared plus 1. Now this is a parabola that's been moved to the left by 1 and stretched vertically by a scale factor of 2. So let's convert this to a parametric equation. We know that t is equal, well, we're saying let t equal x plus 1. So that means y is 2t squared and x is just t minus 1. Done. Now, these rules for transformations apply only to simple equations. We're about to learn some rules of how to graph easily equations without having to convert it into Cartesian form, but they only apply to simple equations. As soon as an operation occurs to t, such as t having something added to it before being squared, before the main function occurs, then we need to find the Cartesian equation. So for example, x is t minus 1 and y is 2 plus 3 actually moves y as x squared 4 units to the left. Not what we would expect. So here we can see that something has happened to the t before it's been squared. So something has happened to it. We can only use these tricks if this was just x equals t here. So this equation here, in each of the equations, nothing is happening to the t. The t has been left alone. The operation of t is not changing. So we can apply these simple tricks. If this was 2t here, it wouldn't work. So this is actually a circle. It's been moved to the left by 2 and up by 1. And this is the radius, which is the radius of 3. So the x coordinate, don't think of it in terms of, it's not this, it's not x minus 2 squared plus y plus 1 squared equals 9. It's not that. We're not moving it that way and down. You're just looking at the equation. It's being x is being moved that way by 2, y is being moved up by 1, and that's because it's in parametric form. If this is totally confusing you, just convert it into Cartesian form using x squared plus y squared is equal, sine squared x plus cos squared x is equal to 1. So it's a circle with center -2, 1 and radius 3. Oh, terrible. And radius 3. Part 2. Sketch x is 2t and y is equal to 2 squared minus 1. Again, nothing is happening to the to t. The t is here and then it's been put in here. It's not t minus 1 and then it's been squared or cubed. The t is just there hanging out and it's been squared, but nothing has happened to the t before it was squared. So this is a parabola scaled horizontally by a factor of 2 and moved down by 1. And we know it's a parabola based on the table from the beginning of this video, the fact that when you have a t and then a t squared for y, it's a parabola. So it's a parabola that's been stretched and then it's been moved down by 1. Now again, if that's totally confusing you, just convert it into Cartesian form. So t is equal to x on 2, which means y is equal to x on 2 squared minus 1, which is a quarter, x squared minus 1. If you want to find the x and y intercepts of that, you're going to get x is equal to plus or minus 2. So this is a parabola moved down by 1, and the intercepts are plus or minus 2. And that's minus 1. But we can see that t is from minus 1 to 4. So when t is minus 1 here, x is minus 2. Sorry, from 1 to 4. So when t is 1, x is 2. And when t is 4, x is 8. So we're only graphing this function, this graph from 2 to 8. Now, when I draw these, I like to just include the rest of the graph in a dotted line. You're welcome to do that. It shows the marker, hey, I know this graph looks like this, but it doesn't exist because of these parameters. And we're stopping at 8, and it's going to be 15. So 8, 15. Okay. The third example, we're sketching x is cos 2t and y is 2 sine t. 2 cos t and y is 2 sine t. But we've taken the absolute value of each of those. Let's just think, okay, the absolute value makes everything negative positive. So first of all, it's a circle, of course, of radius 2. Radius 2. Let's draw a circle of radius 2. If we make everything negative here positive, so all of our x negative values make it positive, let's get rid of them because they've just been reflected and they're just being moved to here. So really it's just the same thing. So we're putting that over there. We're kind of like folding it in half, putting those values over. And then let's make all of this, because we're absolute valuing the y as well, move it up here. So we're reflecting it and getting rid of it and moved up to there. So that's our circle there. Just a quarter of a circle or half a semicircle. Okay. The next thing, and I love this part of the course, are spirals. It looks a bit scary, but I think they're quite cute. So a spiral can be thought of a point moving around a circle, but where the radius is increasing. So there are many types of spiraled, and we're going to cover the simplest, the Archimedean spiral, in this next example. Now, when we're sketching spirals, it's best to consider a pattern and we'll do that a table of values. And yeah, usually I don't like tables of values, but for spirals we're going to use a table of values. So since it's t cos t and t sine t, so as t increases, it's kind of increasing the x and y, so the radius is increasing. Since it's trig, let's do 0, pi on 2, pi, 3 pi on 2, and what might we do? We might do 2 pi. If we do that, let's just fill in the table. 0, 0, 0, pi on 2, minus pi, 0, 0, minus 3 pi on 2, 2 pi, 0. Okay, we'll draw a plane. So I might go pi on 2, pi, 3 pi on 2, 2 pi, and I'm going to do that the same. Okay, so we've got 0, 0, 0, we're starting at the origin, then we've got pi on 2 for t. Now we're not graphing t, t is just our parameter, we're graphing x and y still, so we've got 0 pi on 2, or do we? 0 pi on 2, x is 0, y is pi on 2. So we're going up to pi on 2. Then we've got minus pi 0. So x is minus pi and we're at 0. So pi 0, pi on 2. Then when x is minus pi, y is 0. So x is minus pi, y is 0. Then we've got x is 0, y is minus 3 pi on 2, so that's going to be all the way down here. And then x is 2 pi, y is 0. Wow. So look at that. We've just got this, 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 this. So it's a spiral. It looks something like that. And we can keep extending that table, so we might want to do, say, 3 pi. Let's go 3 pi. That's going to be minus 3 pi and 0. So minus 3 pi and 0, so all the way over here. So it's like this, 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 something like that. And that's our spiral there. That's really as hard as your two-dimensional curves will get. But just wait and see. Actually, no, there are some harder two-dimensional curves. But wait and see, we're going to do three-dimensional curves next.